Students, today we'll be working on the second day of integration by substitution, and this time we'll introduce a final method that can be used if there is a pattern that doesn't allow you to find the derivative and write it in terms of the derivative dx. So I'm going to start you off with a review problem because it seems like the trig functions are a little confusing as to what should be the u and what should be the du. So you're asked here to find an equation for the function f, and that's just another way of asking you to solve a differential equation. So f prime of x could be rewritten as dy dx. So we're going to rewrite this as dy dx equals pi times the secant of pi x times the tangent of pi x. And then, without me taking another line, I'm going to erase and move the dx to the other side. So we'll have dy equals this expression and then dx. And then we're going to integrate each side. So you see the process of solving a differential equation. So the integral of dy would be y equals, and then we have the integral of the secant of pi x times the tangent of pi x, and we do have pi dx. So this is another example of the angle being more complicated than it's allowed to be. We are only allowed to have x as the angle. So when the angle is something other than x, we will need to use a substitution. So we'll let u equal pi x, and that makes du equal to just pi dx. And after we do the rearranging, I think we'll find that we have exactly what we need. So we have the secant of pi x and multiply that by the tangent of pi x. And then I'm going to move the pi to be beside dx. And we do have the du that we need. So I'm going to change this now to the secant of u times the tangent of u du, and we'll be ready then to integrate. So to integrate secant of u, tangent of u, you might want to think backwards what would have that as its derivative, and that would be the secant of u. So we'll have the secant of u plus c, and then we can resubstitute. So y would equal the secant, and then replace the u with pi x plus c. So that gives us our general equation, and then we can finish up, since the equation is asking us for the specific one when we're at the ordered pair of 1/3 1. We can substitute 1 in for the y, and so we'll have 1 equals the secant of pi times 1/3. So in other words, pi over 3. I'm going to go ahead and write it that way. Plus c, and we are looking for the value of c. Well, the secant of pi over 3, if you work with your trig, you'll find out that that is 2, and then we can subtract 2 from both sides to get -1 equals c. So your final answer, f of x, equals the secant of pi x minus 1. And there's your general solution. On this one, the direct substitution is going to fail, and we have some steps that we can take to work with that. Those steps are called doing a change of variables. So we'll start, as we have been, using the u, because we do have a product that we cannot remove. So u could equal, and we'll start with the expression under the radical sign, so 2 minus x. And as we do that, then our derivative, du, would equal -1 dx. All right, well, as you can see, even when arranging it, I have an x plus 1, and that is not in any way equal to -1 dx. So for change of variables, what you will do then is you're going to solve for x for this first part. So we're going to solve for x. So we could add x to one side and subtract 2, and we'd have x equals 2 minus u. And then for the other part, we could solve for dx. And so solving for dx, we could divide both sides by -1, and we would have dx equals -1 du. And so now we're going to substitute, and our end goal is going to be that we have everything in terms of u. So I'll start off with my integral sign, and I'm just going to start substituting for the x. My x is equal to 2 minus u. So 2 minus u, and then plus 1. And then I have my square root. And I'm just going to write it to the 1/2 power. Now, I already set that up that my square root would be the u. So I know for that I have u to the 1/2 power, because 2 minus x is what I defined u to be. And then I need to substitute for my dx, what I have defined for dx, which is -1 du. All right, so that may look more messy, but actually we can combine terms and do the distributive property and actually have individual terms to integrate. So that's what we're going to do next. So I can combine my like terms. I have, and I'm going to move the -1 to the front, and then I have 3 minus u times u to the 1/2 du. And then I'm going to distribute the -1 and the u to the 1/2. So that would give me -3 u to the 1/2, and then -1 u to the 1/2 times -u would give me a positive u, and I can add my exponents and get 3/2 and then du. And we've now created an integral that has individual terms that we can use the power rule for as we integrate. So this is actually ready to integrate. So we'll have -3, and then u, we'll add 1 to the exponent, so that'll be to the 3/2 power over 3/2. And then we'll have plus. We'll add 1 to this exponent, so that would be u to the 5/2 power over 5/2, and add on the c. So we can simplify multiplying by the reciprocal. So -3, and then the reciprocal of 3/2 would be 2/3. That's going to give us -2u to the 3/2 power. And then we'll multiply by the reciprocal again, leaving us with 2/5 u to the 5/2 power plus c. And then it's at this point that we can substitute in back for the original description of u. So that would be -2, and then substituting, we have 2 minus x, and that would be to the 3/2 power plus 2/5, and again substituting in 2 minus x, and that is to the 5/2 power, and then plus c. Now, there is some further simplifying that can be done, and often is done as we prepare for perhaps finding your value of c, or setting something equal to 0. So I'm going to do a couple more steps of some extra simplifying that can be done, and it involves factoring. So if we factor out the common factor, which is the 2 minus x to the lowest power, 3/2, as well as if we factor out the fraction 2/5, then we can simplify this just a little bit more. And so I'm going to factor out 2/5, and then the 2 minus x to the 3/2 power. And then that will leave us with, now remember, factoring is nothing more than dividing. So if I take -2, I'm going to do some work off to the side here just to help you think about it. If I take -2 and I factor or divide by 2/5, then that would be the same as -2 multiplied by the reciprocal 5/2, and that's going to give me -5. So that first term, I'm going to have -5, and then I factored out the parentheses from that first term. And then I'll add to that. And from my second term, I factored out the 2/5, so that's no longer there. And remember that factoring is dividing. So I took 2 minus x that was to the 5/2 power, and I factored out, or I divided out, 2 minus x to the 3/2 power. And again, this is just some side work to help you think about it. We haven't done this kind of factoring for a while. So I would keep the base of 2 minus x and subtract my exponents. 5/2 minus 3/2 would give me 2/2, or 1. So I have 2 minus x to the first power. And then I can combine my like terms inside that bracket. Of course, I want to remember plus c. And so that brings me to my final answer of 2/5 times 2 minus x to the 3/2 power, and then I'd have negative 3 minus x plus c. And we'll find that that is often a more useful form of the answer because it's all multiplication rather than having the individual addition terms. So that might be something that, as you see my final answers on the homework, I've done some extra simplifying, and I'd like for you to work on that skill. So there's your second example. We'll clear the screen. And that's what we call change of variables. Now, we can also, we'll find out that we can also do a change of variables and actually evaluate definite integrals. So when you do this, you'll need to adjust the limits of integration when doing your U substitution. So let me go ahead and get us started on this. Since I have a quotient that lets me know that I am going to have to use a substitution. So U will equal, I'm going to use my denominator from inside the square root, 1 plus 2x to the second. And so my derivative du would be 4x dx. So as I look at what I have the integral from 0 to 2, and I'm going to rewrite that 1 plus 2x to the second as a negative 1/2 power. And then I'm going to bring the x beside the dx. So I have an x, I need a 4x, so I'm going to multiply by a 4 and balance it with a 1/4. And as long as I'm still writing everything in terms of x, I can leave my limits of integration at 0 and 2. But now my next line, I'm getting ready to rewrite this in terms of the u now. So I'm going to leave off my limits of integration because I'm going to have to adjust those. So my 1 plus 2x to the second is now u. This is u to the negative 1/2 power. And then my 4x dx is my du. So I have something nice and simple that I can integrate. But this is a definite integral. So I have to adjust those limits of integration. So the way that I'll do that is I'm going to treat the u like a function. And I'm going to adjust the lower one first. So u of 0, and this is the lower limit. I'll do it first. So the lower limit, I'll plug in 0 to my definition of u. So that would be 1 plus 2 times 0 squared, and that's going to give me 1. So my lower limit of integration is going to change from a 0 to a 1. And then I want to do the upper limit. So the upper limit had been a 2. I'm going to do u of 2. So that'll be 1 plus 2 times 2 squared. So 2 squared is 4, times 2 is 8, plus 1 is 9. And so my upper limit of integration is now 9. Now, when I do this, I will not re-substitute. Once I've made this adjustment, then we will use the power rule and not re-substitute. But we will use the fundamental theorem of calculus. And I'll just abbreviate that, fundamental theorem of calculus. All right, so let's do the power rule. So we have 1/4, and then u will add 1 to the negative 1/2. That's going to make 1/2 over 1/2. And then this is evaluated from 1 to 9. So I'll simplify that. I'll have 1/4 times the reciprocal of 1/2. So that'll be 1/4 times 2. And so that'll end up being 1/2. And then I'll have my u to the 1/2, which is the square root of u. And I'll evaluate that again from 1 to 9. And now I'm ready to use my fundamental theorem of calculus. So I have 1/2, and then the square root of 9. This is f of b minus f of a. So 1/2 times the square root of 1. And so that would be 3/2 minus 1/2, giving me 2/2. And my final answer is 1. So you can do this change of variables. You can do this substitution process with definite integrals. But when you do, you must adjust the limits of integration. Do not resubstitute back to x, and do use the fundamental theorem of calculus. So there you have that example. I have one last little theorem that I'm going to share with you about even and odd functions. And this is just a matter of a time saver for you that we're going to throw in. So if you have an even function and you are integrating that function from negative a to positive a, then it would usually be easier to just integrate that function from 0 to a and double your answer. So again, you have an even function, you're integrating from negative a to positive a. You can simply integrate from 0 to a and then double your answer. It's much, much easier to apply the fundamental theorem of calculus using a 0 than it is to use a negative a. And then likewise, if you have an odd function and you integrate from negative a to positive a, and I think you saw this as we were looking at integration as area, then the antiderivative is just going to equal 0. So if you notice that you have an odd function and you're integrating from the negative of a number to the positive of that same number, then your integral is going to be a 0. So just very quickly, I'll do this last problem. I'm not going to do it by substitution, but I am going to notice that I have something that I can multiply out. So I have the integral from -2 to +2 of x to the 4th plus x squared dx. And that is an even function. All of the exponents are evens. And so rather than continuing with that integral, I can change it to the integral from 0 to 2 of x to the 4th plus x squared dx, as long as I double my result. So as long as I multiply by 2. So applying the power rule, I'll have 2 times x to the 5th over 5 plus x to the 3rd over 3. And then this evaluated, should have used a bracket there, evaluated from 0 to 2. And so you'll see that as we substitute in, that we have 2 to the 5th over 5 plus 2 to the 3rd over 3 minus, and then plugging in 0, I get 0. So you'll see that that was much easier than plugging in the -2. So then just simplifying that out, my 2 to the 5th is 32. So I'll have 32 fifths plus, and then 2 to the 3rd is 8. So 8 thirds. And when you get your common denominators, you get 96 fifteenths added to 40 fifteenths and then multiplied by 2, and your final answer, 272 fifteenths. And although that took a little bit of effort, it certainly took less effort than working with the -2 as part of the integration process. So this is actually your last integration technique before we jump into our next unit, which will involve logarithms. So we're going to wrap up this unit with this lesson, and make sure that you are staying up on your homework and asking questions as you need them.